So we've already talked about advection or bulk movement with flow or flux density. And here we're going to talk about spread and mixing processes. There are a few different kinds. There's diffusion, molecular diffusion, turbulent diffusion, both kinds of random mixing. And then there's also dispersion, which is not random, but the result of it kind of looks random. So people often think about it as being random, even though it's not really. Here, in this video, we're just going to talk about diffusion a little bit. It's also called Fickian transport. You might hear that word sort of bandied about in the environmental consulting world. It's a good thing to know about, apparently, when you go in for interviews, that sort of thing. But here we're mostly going to talk about diffusion. So diffusion, you're probably used to thinking about it or have thought about it before. And I'm going to start this video here because it takes a while. And you can watch this clock up here to see how long diffusion takes. So this is the spread of particles through random motion from regions of high to low concentration. So it only occurs when there is a gradient in concentration. So if the molecules are evenly dispersed in an area or a closed system, then there's no more diffusion. You're done. Okay, but in general, you can see this takes a long time. If you look at the clock over here in the corner, here we've got 9 hours, 10 hours. So this takes a long time. It's not a fast process. And if you move all the way to the end, you can see you're still not done. It's been nearly a day. Okay, so not quick. Okay, there's also a little video tutorial that you can look at here. I'm not going to click on it here. I have a link to it in Blackboard, so you can check that out if you would like a little reminder. But the idea from this tutorial is that bunched up molecules bump into each other more, spread faster than those that are further apart. So when there's a large concentration gradient, or when a whole bunch of molecules are bunched up together, then they spread a little bit quicker than those that are already a little spread apart. Or in other words, the rate of diffusion is directly proportional to the steepness of the concentration gradient. And this is also known as Fick's first law. So this is kind of where that Fickian transport idea comes from, or where the name comes from. Okay. So if you're looking at these two boxes here, A and B, you can pretend that they're filled up with water and these are molecules in them. Which gradient is steeper? So you can pause and think about that for a moment if you like. And the answer to that would be this A box. It has a steeper gradient because all of the molecules are bunched up together here. If you look at how many are here, there's a lot of molecules in this area here and really none over here. So that is a steep gradient. The steeper the concentration gradient, the bigger the change in concentration over space. So here, if you were looking at basically the same spot here, you'd have a lot here, but then you'd still have some over here. So that is a less steep gradient. And a steeper concentration gradient then means faster diffusion. So that is Fick's first law. Okay, and here is what that kind of looks like. How do you figure out the gradient? This is kind of what that looks like in a math world, which we do spend some time in this class. You look at the change in concentration over the change in distance. So that's what that looks like in words, and you'll also see that change in symbol here being the triangle. So change in concentration over change in distance. So how would you go about doing that in this example here? I've estimated there are about 12 particles here, so this is the to get the change in concentration gradient, you do the second concentration minus the first concentration. Here I have those values here, and the second distance minus the first distance over here. So here you've got 0, that's C2, minus 12, Z1, or C1, sorry, and then 11 centimeters, X2 minus 1 centimeter, which is X1 over here. And you come up with a negative concentration gradient, right, because you're going from high to low. That's negative 1.2. And you do the same thing over here. So it's a bigger number, right, than over here. You do the same thing. You start out with 7 at 1 centimeter and go to 2 at 11 centimeters, 2 particles, I'm saying, in that little box. And you come up with a concentration gradient of negative 0.5. So the bigger number is the steeper gradient. And that makes sense when you look at it in terms of what these pictures look like. So there are a few different ways to determine a concentration gradient. One is the one I just showed you below, using 2 points. So, x1 and x2 and the concentration of substance at those 2 points. Or you can get multiple samples. So I'm going to show you that here. So this is the concentration. I'm saying there are about 8 particles in this little box there. Then you can go to 2, and you have 7, 6, 5, 4, 3, 2, 1. Right, so now you have a line, essentially. So you have samples at multiple points over space. So how would you use that information to get the concentration gradient? In this case, you would just use the slope of the line. That's the same thing. It's the change in concentration over the change in distance. So that's what this would look like. You could just pick, this is a straight line, so you could pick any 2 points on this line and calculate the slope. So rise over run, right? Change in y over change in x. Okay, so this might seem somewhat familiar to you if you remember your calculus. A derivative, and here's a question for you. A derivative is closely related to which of the following notions? That it is A, a set of solutions of an equation, B, the slope of a function, or C, the zero of a function. Okay, and you can pause and think about that for a moment. Make a guess. And the answer would be the slope of a function. So if this is sounding very unfamiliar to you, I encourage you to go look at the calculus review on Blackboard under week 3. Okay, so if the equation for the function below is that for a straight line, so that's y equals mx plus b, then what is the derivative in this equation? So would you think it would be m, the slope, which is also change in concentration over change in x, b, the intercept, where x is 0, or 0? So you can think about that for a moment, make your choice. And the answer would be the slope, right? We just talked about that. So the derivative is the slope in that equation, which is m. Okay, so below, I encourage you to pause and use these values here for x and y, which in this case is distance and concentration. And again here, distance and concentration, to calculate the slope of this line. So what would that be? And the answer is -1. Pretty straightforward linear equation. I wanted to give you all whole numbers to work with, so hopefully that wasn't too tough. Okay, so this isn't worth any points. I'm not sure why I left that in there, but this is just an example for you. So if you wanted to calculate the gradient of chloride across the freshwater saltwater interface in an estuary, so this is essentially the salt gradient across a freshwater saltwater boundary, where the chloride concentration changes from 20 to 2 grams per liter in a distance of 5 meters. So if you had a problem like this, hint, hint, you might do something like the below. So you take C2, which is 2 grams per liter, and subtract C1, which is your first number, which is 20 grams per liter. And you could also do, think about C1 as being 0 and C2, or X1 as being 0 and X2 as being 5 meters. So this could be 5 minus 0, or you can just use the total distance here and have 5 meters there. So you can work that out to be -18 grams per liters over 5 meters, or you can do all the math out and say it's -3.6 grams per liter meter. Okay, so that is your example using 2 points. Oh, I don't mean that that's worth 2 points. It's using 2 points to calculate the gradient, the concentration gradient. Okay, and right, that just shows you the same thing again. Okay, so there are a couple different ways of determining a concentration gradient. The first is using 2 points, as we just did in that example. The other is using multiple samples, and as long as that line is linear, as it is below, you can just use the slope of that line. Or if you have a nonlinear function, which is actually what's going to happen most frequently if you're in a, particularly if you're in a river or even in air, this is what's going to be most typical, is you're going to have a nonlinear function if you take, or a nonlinear line here, if you're going to be taking multiple samples. So what do you do then? In this case, you go a little bit back to your calculus again, and you want to take the slope of a tangent line at the distance that you're interested in. So what might that look like? You could take a slope of a tangent line here. You would just draw that and calculate the slope of that. And we're going to do this in class. I'm not going to go over it too in depth here. This is what another tangent line might look like at that point, at this point. So you can see you can get different concentration gradients depending on what point you're interested in, or what distance you're interested in. Okay, so to kind of sum up, Fickian transport is diffusion. Random mixing, the rate of diffusion is directly proportional to the steepness of the concentration gradient, and that's Fick's first law. And of course, there's a mathematical model for this, and we'll deal with that in class. And we talked about a couple different ways of calculating the concentration gradient using 2 points, the slope of a line, and if a line is nonlinear, then we're going to be using the slope of a tangent line, and we'll do examples of that in class. And then in class, we're going to get a little more specific about the different types of diffusion, different types of mixing with some examples and more sort of real-world problems. All right, so that's the last video for today, I promise. And thanks for watching.